So today we're going to continue talking about derivatives and getting used to this big idea. But the big focus of today is also trying to connect it to an idea we talked about before that was continuous. So recall our gut definition was that a function is going to be continuous as long as you can draw the graph and it has no breaks. You don't pick up your pencil as you draw it. So let's get talking about this. But first we need to introduce a new idea, and that is what's called the alternative form of the derivative. So the alternative form of the derivative says that if you have a function defined at a particular point, then define the slope at that point, all we have to do is compute this quantity we have on the right. So first we set up what looks like a difference quotient, and again we take the limit, and this is going to be the alternative form of the derivative. So let's draw some graphs and see what's really going on here. So on two graphs here we're going to compare the different definitions of the derivative. So on the left graph, we had a point we wanted to figure out the slope at, c f of c. And so what we would do is we would pick a point some distance away from it, and we called it c plus h. And we grabbed that point on the graph, which has coordinates f of c plus h. And we said, well, if we compute the slope between these 2 points, what we want to do is we're going to take the limit as h approaches 0 of f of c plus h minus f of c all over h. And as we bring these points together, as we make h smaller, this will get us a better approximation for the slope. So now what we're doing instead is now we're picking another point on our graph, f of x, and we're setting up a limit that says we want to take x as we approach c of f of x minus f of c all over x minus c. Well, what's this f of x minus f of c part? That's just our vertical distance here. That's our rise. And x minus c here in the denominator. Once again, what's that? That's just our horizontal distance there. And all we're doing here is we're saying the limit part says, well, let's take x here and move it on over. And as we move these points closer and closer together, it's going to compute the same thing. It's going to compute the slope. This form is just easier to use sometimes than the other form. They'll both give you an answer. Both of them work pretty well. This one just sometimes makes factoring a little bit harder to do, but in some problems it makes it a bit clearer. Alright, so let's take this new limit definition out for a spin on a function we already know how to compute the derivative of. Remember, previously we already computed that the derivative of this function is just going to be 2x, so let's just check and make sure our new definition works well. So the first step is just abstract setup. We say that our derivative is going to be the limit as x approaches c of our difference quotient. So again, it's rise divided by run. We make the distance we're running smaller so that we get a more accurate answer, and now it's just abstract. Next, we want to use our actual function x squared. So here we actually use the fact that f of x equals x squared. And so all we did was we put x into our function for x squared, we put c in, and we get c squared. And now here's the point where we want to try to compute our limit. Problem, of course, we can't directly sub. If we just put c in here for x, then we're going to get a divide by 0. So of course we need to try and factor and cancel something. And so this one's not too bad. It factors pretty nicely as x minus c, x plus c. So we used it, we can factor. And of course, when we factor correctly, we're going to get this part to cancel off. So the x minus c's will cancel. And what we're left with is a really nice, easy limit to compute now. Now we just need to go ahead and we replace all of our x's with c. So now we get c plus c all over 1, which gives us 2c. Now the usual way we're going to write this, though, is we're not going to leave it in terms of c's because for some reason people don't like c's. So what we say is we say that our derivative f prime of x is equal to 2x. We just change all our c's back to x and we're good to go. And we see that this matches the other way we computed the derivative. So here we go, we've got our function that gives us the slope everywhere again. Good job. Limit Man is proud of you. So what we're going to do is we're going to work through a few other examples to see what this new definition can tell us in terms of functions. And the first thing you want to do is you want to look at this graph here, and you want to think to yourself, if I look at this graph here, what would I guess the slope is going to be if I took the derivative at 0? If I try to find the slope at 0, what do you think would happen here? What's my slope? So just take a minute, guess. Is it going to be 1? Is it going to be 50? Is it going to be 0? What do you think it's going to be? And then we'll work through the limit to see what actually happens. So no cheating. I really hope you made a guess. But let's go through this. So we always start with the abstract difference quotient to begin. And now we actually want to use our function to see what we can figure out here. Well, there's not much that can be helped really. The only thing we know is we have that since we know that g of 0, well, we got to use this top part of the piecewise function is going to be 1. This is all we really get. So we don't get anything too great out of it because we need to use different functions if we use from the left or right. But we know how to do this. We just need to figure out now the limits from the left and the limits from the right. So first we'll compute our limit from the right. So our limit from the right says, well, we need to think, well, what happens if we put numbers into g of x that are slightly bigger than 0? In that case, we use the top rule of our piecewise function, which says that we're always going to be 1. So if we always start on the right of 1, we're over here. And so what that means is we need to come in and we need to be positive 1. So that becomes 1 in our limit. Everything else stays the same. Well, I can take 1 minus 1, I get 0 over x. And so when I take the limit, I'm going to get 0 here. So this means that basically our slope from the right is kind of 0. Okay, it's coming in there at 0. Slope from the right is 0. Well, what about the slope from the left? Now, if we're coming in from the left-hand side at 0 there, now our g of x function, we need to use the second part of our piecewise function. So that's why the g of x here becomes negative 1. Well, that means we're going to get a negative 2 over x overall. So when we compute this limit, well, we're going to have a negative 2 divided by a really, really small negative number, which means we're going to go off to infinity. Now the problem here is if you look at the graph, there is no place where it looks like we have infinite slope. But what's happening? What's happening is we're trying to compute the slope from a point down here on the graph to this point right here. And that we can see that's a positive slope. And what we're going to do is we're going to move this point closer and try again to compute this slope. And we're going to compute the slope there. It's a little steeper, it's a little taller. Well, as we get closer and closer, the slope we're trying to compute there gets steeper and steeper and steeper, so that's why it appears to give the answer of infinity. Now actually this is junk. What we're going to say here is this doesn't make sense and the slope is not defined. So the slope doesn't exist here, the limit doesn't exist, so the derivative does not exist. At 0. Now it's an important point to note here. It doesn't exist at 0, but you can totally find the derivative anywhere else. Pick a different point. Pick this point right here on the graph. The slope here is 0. Pick another point. The slope here is 0. Pick another point. The slope here is 0. Any other point you pick, the slope is 0, but at 0, we have a problem because this graph isn't continuous, so it doesn't give us a good answer. So here we're going to look at another example. We're going to look at to try to find the derivative of h of x equals the absolute value of x at c equals 0. So take a minute to guess to yourself, well, what do you think is happening here at 0? You know, what do you think the slope is here? Over on the right side here, if we picked a point here, it's not too bad to calculate that the slope should be 1. And over here on the left, the slope should be negative 1. So maybe it makes sense to call the slope 0 down here. So what do you think it's going to be? What does it look like to you? Alright, let's figure it out. So as always, we start with our abstract setup, and now we try to use our function. So we put everything into the absolute value function. We get the absolute value of x minus the absolute value of 0, and of course we can simplify this down a little bit. Now the problem is we can't just cancel this, because it's a secret that absolute value is really a piecewise function in disguise. The absolute value of x will be x if x is greater than or equal to 0, and it's the opposite if x is less than 0. So it really is a secret piecewise function in disguise, and so what we need to do here is we need to use different pieces depending if we're going to come from 0 from the positive side or the negative side. So we really have to compute two limits. So first let's think about what's happening from the right side. So if we look at the positive side of this function to the right of 0, well, that looks like just like the graph of x. So that's how we got from the absolute value of x we can replace with just x, in which case x over x definitely nicely cancels. So we get the limit as x approaches 0 from the right of 1, which just gives us a slope of 1. And this kind of makes sense. If we look over on the right side of the function, this kind of looks like the slope would be 1 if we picked a point down here and moved it close when we're calculating the slopes. But what happens from the left side? So the problem is that when we look at from the left side here as we're coming down, here the absolute value of x looks like negative x. So absolute value of x gets replaced with the negative x, the opposite of x. And so now when these cancel, we're left with a negative 1, which means our slope is negative 1. So these means that our slopes from the left and the right of our derivative don't agree, okay? And since these don't match, once again, it doesn't make sense to talk about the derivative here because it doesn't exist. Just to reiterate, the derivative of the absolute value of x does not exist at 0, okay? We can't make sense of the slope here because it's kind of a corner. It doesn't have a nice smooth curve to it. Whereas everywhere else, we got a slope of negative 1 over here on the left. We have a slope of negative 1 here on the right. So this means the derivative does exist sometimes. So really what we could do is we could write that the derivative of our function here in good old Leibniz notation is really a piecewise function, and it's 1 or negative 1. It's 1 if x is positive, and it's negative 1 if x is negative. So our derivative exists, just not at 0. So here is one last example of something to watch out for as you try to take derivatives, okay? And it's going to be this function k of x equals x to the 1/3 at c equals 0. So again, we're talking about right here, what's the slope of this line right here? Well, what you should do is you should try to guess, but you always think to yourself the same thing. Well, what we're going to do is we're going to pick a point on the curve, and we're going to go towards it, and we're going to try to move this point closer, and we want to think, well, what does it look like my slope is doing there? What's happening to these slopes as we get closer and closer to 0? So what do you feel in your gut? Alright, now let's see if your gut is correct. So hopefully, after your gut made a guess, it said, well, we need to go through our abstract definition again, setting up our difference quotient and taking the limit as x approaches 0. We substitute everything into our function here, into our function x to the 1/3. The 1/3 root of 0 is 0. So now we just got some algebraic simplifying to work through. And so now we need to compute the limit as x approaches 0 of 1 over x to the 2/3 power. Okay, so this one takes a little bit of thinking through. What's going to happen here is we're going to put small numbers in here. And these small numbers, what's going to happen is they're still going to continue to grow. X to the 2/3 grows pretty slowly, but it still grows. And so what we have is it's 1 over small, always positive numbers. And so we end up with a limit of infinity. And that's kind of what looks like is happening here. It kind of looks like our tangent line here is vertical, that it has infinite slope. And that's exactly what happened here. We had ourselves a vertical tangent line, infinite slope. So we're going to say that the function has a vertical tangent line at c equals 0. Now, it's important little note that the derivative does not exist here, okay? The problem here is that we want our derivatives to be actual real numbers. Infinity is not a number, it's an idea. So realistically, it doesn't make sense to say the derivative is infinite. It makes sense to say the slope there is infinite, it's a vertical line, but people don't like you going around saying the derivative is infinity. It's just considered not very classy, I guess. But that's okay. So the last thing we want to talk about today is how these two ideas we've discussed, differentiability and continuity, work together. Or maybe they don't. So let's look and recall some examples we've looked at so far today. So this was one of the functions we looked at. It was -1 if x was negative, +1 if x is positive. And we found out two things about it. First of all, visually we can see it's not continuous. And we also figured out that it was not differentiable at 0. Everywhere else was good to go on this function. It was continuous and differentiable everywhere else, but at 0 it wasn't continuous and it's not differentiable. Now we also looked at the function the absolute value of x, and in this case at 0, well, it is continuous. That is, we can draw this graph by sloping along here and then just changing directions, but we never have to pick up our pencil or pen or whatever, so it's continuous everywhere, but it's not differentiable at 0. And so what this leads to is the following important theorem. So the theorem says that differentiability implies continuity. If you have yourself a function and you can take its derivative somewhere, that means that function had to have been continuous there. Okay? If this idea of slope makes sense, then it had to be continuous. Okay? If slope makes sense, there's no breaks at that point in your graph. There could be breaks other places, but as long as you can find the slope, it's got to be continuous. Now it's important to note the other direction doesn't work. We have an example right here where our function is continuous at 0, but it's not differentiable there. We can't find the slope. So let's give a quick talk about why differentiability implies continuity. Okay? So recall the definition of continuous. We need to show somehow that the limit as x approaches c is actually equal to the value that you achieved there. That is, if you're going along on your graph from both sides as you get closer to c here, well, what better happen is both sides of this come together, that's the limit part, and that actually equals the function value there, because that's what makes it continuous. You fill in all the holes in your graph. Well, in order to show this, what I'm going to do is I want to show that the limit as x approaches c of f of x minus f of c, my goal is to hopefully show that this is equal to 0. Because if this thing equals 0, that means I have exactly what I wanted, that the limit equals the function value there. So let's see how to do this. So the first thing I can do is I can rewrite this limit by just multiplying by and dividing by x minus c. Nothing too tricky going on here. Those things would cancel, and limits don't care about this stuff. As long as these things cancel, these are definitely going to be the same limits. But now let's look at what happened. What's this guy in parentheses? What does that look like to you? What is the limit as x approaches c of that piece right there? Well, after we bring the limit closer, hopefully this piece over here looks to you very, very familiar. That's just our derivative at c. And what happens over here? That's a nice polynomial. What's the limit as x approaches c of x minus c? Well, we're just going to replace this x with c, take c minus c, and get 0. And so what do I end up with? Well, I end up with 0 times some number. 0 times a number is fine. That's just a 0. So overall, what I figured out is I figured out this limit here is equal to 0. Now what's the big deal with this limit? Well, what I can do is I can break this up at the minus sign here into two separate limits. And then I can compute these limits separately. Well, this first one just says replace your x with c. That's your nice limit. And this other one, well, there's no x's to replace. That's just a number, so that's just going to be f of c. And so now all I've got is that the limit minus f of c equals 0, and so what I can do is I can simply rewrite this as the limit as x approaches c of f of x is equal to f of c, which means our function is continuous. So if you can take the derivative, it's going to be continuous. Now this is most useful in the other form that we'll see an example of next. So the way the theorem's really used is it's used by taking what's called the contrapositive version, which means we switch directions and negate. But what it means is if f is not continuous at c, then it's not differentiable, okay? So anywhere that your graph is not continuous, it's not going to have a derivative. It's out of luck. Now there are other places where it's not going to be differentiable. So let's take as an example this graph here. So suppose we want to figure out where is this function going to be differentiable. Well, what we do is we start on the left and we say, well, starting at -3 here, okay, this looks pretty good. Slopes make sense here. We're going to imagine it keeps going and say the slopes make sense. Well, they pick up again here, but what we had to do is we had to make this jump here. It wasn't continuous here at -2, so that means to start with, we're going to say that it's differentiable from -3 up to -2, and then we start again at -2. Well, we follow the graph along here. Here, at -1, it has to make a jump again, so it's not going to be differentiable there. It doesn't make sense to talk about the slope here at -1. So we're going to mark -1 here, and we'll start again at -1. Now what we get, though, is now we get something nice. From -1, slope's looking good. 0 slope here, but that's fine. These slopes all look good until 1. It's still continuous here at 1. However, that sharp corner tells me that we're going to get different kinds of things if we look from the left and the right. We're going to get different limits there, so the slope doesn't make sense. It's not going to be the same from both sides. Therefore, 1's out. And now we can start picking up again from 1 to, what is that, 1.5. Once again, the slopes seem to make sense. So these are the key features to look for. You want to look for breaks in your graph, jumps, or nice little corners here. Any of these things, breaks and corners, are what really wreck the ability to compute derivatives, and therefore it's only going to be differentiable at the other points. As always, try the questions before class tomorrow, post a question to Blackboard, and ask me any questions that you have. Thanks.